All right, well, good evening and welcome to Lecture 7 of MT225. Let's see, so tonight we're going to be continuing on equilibrium problems. We'll be working out a few more examples here to illustrate some of the tricks that can come up or some of the tricky situations that can come up and how we can use the mathematical skills we've learned so far uh, to make sure that we've got the right answers and that we've got reasonable answers. So first, of course, contact information. That's all pretty standard at this point. Homework 2 is due this evening, due by midnight tonight. So make sure you get that in if you haven't submitted it already. I'll open up the floor for questions on that assignment in just a moment. Homework 3 has been posted, and that is due next Wednesday, same time. So that is March 3rd. So we're into March already next week. Quiz 1, I emailed back the results on quiz 1 yesterday. So if you didn't receive email back, then that means I didn't get a quiz from you, or I didn't get one on time. If the quiz didn't go so well for you, which it went well for most people, but if it didn't go so well for you, don't worry too much. Remember that the lowest 2 quiz grades are dropped. So there's plenty of space to make up for a little bit of lacking performance. If you happen to miss it or got it in late, you'll be able to recover from that fairly easily. Major points on quiz 1 were significant figures. That was what bit a few people. You got to read the questions carefully. If there's a statement about significant figures, then it's required. It's part of the specification of the problem. You have to say something about the number of significant figures that you're using. In that, both the problems on the quiz, we had 3 significant figures, what we wanted, and so you had to state your answers to 3 significant figures. And so that was a point that we reviewed a little bit last time. So those who waited till after class to do the quiz may have had that a little more fresh in their memories than those who maybe didn't. So be aware of that. Quiz 2, we will have a quiz on the content for homework 2 next Monday night. So same setup for now. We'll go ahead and post it sometime, probably Sunday afternoon, and it'll be similar to the work you did for homework 2. Speaking of homework 2, does anyone have any questions they'd like to ask on homework 2? Anything that didn't make sense or that you want to see worked out before you officially turn in your solutions?
Yeah, so for the last question, problem 3, can you give us an example of what work do you want to see, or just our answers, or
Okay. Well, let's take a look here. So I just so happen to have a copy here. So we'll go ahead and take a look at that. So there's problem 3, which was a vector addition problem. And the question states to find the sums in both the component and the magnitude and direction forms, and to state your resultant directions in terms of an angle measured from the nearest convenient axis. So that pretty much leaves the door open as long as if you provide a picture, it usually answers everything. But be sure to specify your reference axis or provide a drawing. So what I was trying to avoid here was having people say, well, my answer is 32.3 at 37 degrees. Well, when you just say 37 degrees, I don't know where that 37 degrees is referenced from. If it's from the positive x-axis, negative x-axis, from positive y, and in what direction, clockwise or counterclockwise. This isn't a math class where all angles are always measured counterclockwise from the positive x-axis. That is the default interpretation. So if you just give me a magnitude and a direction, I'm going to assume it's swung from the positive x-axis in the counterclockwise direction unless otherwise stated. So what I would do to make sure everything was perfectly clear, because a lot of engineering is about communication. What I would make sure we do is draw a final picture. So Unless, well, does anyone who is online right now, were there any of these that you wanted specifically to see worked out, or was it just more of a question of format for your answer?
For me, it was just format.
Okay. Well, unless anyone else speaks up on it, I'll just I won't do the math, but I'll show you what I would generally, how I generally format an answer. So let's take C plus D. So this would be F. So C, we have a vector of magnitude 13, 45 degrees clockwise from the negative x-axis. And then we had vector D down here somewhere, also magnitude 13, but at 20 degrees. Now, in the process of figuring out what the vector sum is here, you would break your vectors up into components. So you'd have an x and a y component for vector B, or vector C, and you'd have an x and a y for vector D. And somewhere over here, you'd do a sum in the x direction and a sum in the y direction, and you'd get a couple numbers. In fact, since I won't work out the math, but I will put the right numbers in here. So you'll at least get a confirmation on that. Let me just pull up the solutions here, which will be posted tomorrow. There we go. All right. So for F, when you do your sum in the x direction, you'll get negative 21.412. And when you do your sum in the y direction, you'll get a positive 4.746. Does that match up with your component numbers?
Yeah.
Okay, good. So that eliminates all the sines and cosines and the adding and subtracting and all that. So this is where you'd end up with. So this is part way to your answer. In fact, it satisfies the part of the question that says to state your answer in terms of components, because you've got your component values right here. So you know that your resultant vector has an x component that is 21.412 to the left. So how I would write it out, I'd draw it out just like this. I would say I've got 21.412, and I'm using that negative sign to point it to the left. That would be my x component. Then I've got my y component, and I draw my y component right in where I left off, right there, roughly to scale, and label it 4.746. So those are your two components. Your net x component was 21.412 to the left. Your net y component was 4.746 up. So that satisfies the first part of the question. To get the magnitude and direction, you have to add those two vectors together, which is effectively forming that hypotenuse. Since 21.412 to the left plus 4.746 up is going to give you some magnitude at some direction. And if you always draw your x component first, then your y component, generally you'll always get an angle reference to horizontal. If you draw y then x, you'll get an angle that's referenced to vertical. Either way, it works, and either one's correct. But remember those two answers. If you reference your angle to vertical versus horizontal, those are going to be complements of each other. So one of the big errors I see in this problem is not so much an error, but being unclear about what angle is being used. I like the drawing because it immediately identifies and shows me exactly what angle you're talking about. So you don't have to bring in any words saying, well, this is clockwise from the negative x-axis. It's right there in the drawing. So it's perfectly clear what it is. So all that's left is to get the numerical values for that. And the magnitude you'd get from taking your square root of your opposite squared and adjacent squared. And if you work that out correctly, your magnitude should come out to be 21.93. And then your angle you'd get from your inverse tangent of the opposite over adjacent. So 4.746 over 21.412, which is going to give you a small angle, 12.48 degrees. So that's about where you'd end up there. So that would be your magnitude and direction. So you'd write those in here, 21.93, and your angle of 12.48. There were no significant figure restrictions in this problem, so usually 4 or 5 sig figs will do fine for it. But this right here, this picture right here has everything. It satisfies all the objectives of the problem. Tells you your components, has the right directions built in, has the magnitude and direction. The problem comes in, problem I usually see with this is when people try to get away with not drawing the picture. And it's just a lot easier to draw the picture. So I'd strongly encourage you to just draw it out. That answer your
Okay.
question?
Yeah, makes more sense now.
Okay.
Thank you.
I got a
Any
quick
other
question.
homework questions? Doug?
Yeah, like on that problem, do we have to put like 4.746? Do we have to label each side if we have the numbers elsewhere in the problem?
No, you don't have to. As long as you've got it somewhere like this up here.
Uh,
And again, the default interpretation is where things fall in if you don't have a picture. So you've got to be careful if you're doing something not quite standard. For example, here, if I see a negative on an X component, I'm going to assume it's pointed to the left. That's the default interpretation of a negative. We're going to see tonight that negatives don't always mean left or down. They can mean opposite. And so we have to be clear about what we're doing with that. So again, usually a picture makes sure things are clear. But as long as you've got the numbers there, even if you have the numbers somewhere else and you have the directions drawn out, as long as you've got enough pieces of information there that show that this X component's to the left and the Y component's up, then you'll be fine.
all right. My numbers are slightly off just by like I think a couple hundredths.
Is it that last last digit? Like
Like I got
21.92 or something like that?
21.408.
That's a little much for round or for just round off error. Usually if you round off, if like I kept my internal numbers here to 5 sig figs, you'll throw off that 5th sig fig, maybe the 4th one, but you usually won't be off by that much. Usually you should be able to round it down to down 1 sig fig and it'll match. Here, even if I round the answer number you just gave there for that, you had 21 point, what did you say it was?
I'm talking about the sum of X.
Okay. Yeah, I got you. 21.4.
Yeah, I had 0.8.
Yeah, that's
I'll have to go back. I can go back
that's fine. I would because I used 4 sig figs here. I put 5 in this one, but I used 4 in this one. If you have to round it down 1 or 2 sig figs to match it, it's probably fine.
Okay.
21.4 is what you'd get if you rounded yours off to 3 sig figs. This is also 21.4 to 3 sig figs. So that's probably just round off error.
All right.
Any other questions there on any of the homework? All right, then. Well, let's proceed. So tonight, our objectives are going to be to practice a little bit more with equilibrium problems for concurrent and coplanar force systems. So nothing much really in the lecture notes other than just a framework for us there. So let me briefly review how we solve an equilibrium problem. So when we've got some sort of equilibrium problem, what we're looking at is a number of forces acting on an object. And if that object's in equilibrium, then that means that those forces add up in a vector sense to 0. So when you add all the x components together, you get 0. When you add all the y components together, you get 0. It's a tug of war that no one's winning. In equilibrium problems, we're trying to figure out usually either one force in both magnitude and direction, or maybe a couple forces where we know the directions, or a couple directions when we know the forces. We're trying to find two missing pieces of information that, if they're the right values, will make the system be in equilibrium. And we did a few examples last time, and if those were problematic for you, hopefully you spent some time going back and reviewing the video. That may help you out with the procedure and keeping your information straight, because they do get a little more complex from here. The examples we did Monday night were pretty simple, and I set them up that way to make sure that we could really get a handle on the procedure and the principles involved. Tonight we'll do a couple things a little bit different. Same basic procedure, same basic principles, just a couple of traps that might be in the math or in the setup that could cause problems if you're not aware of them. So let's start out with another box on a wire problem. This one will be a little bit different than the one we finished up with, or that we worked on last week. I'm going to take some sort of weight. Let's make it 1,200 pounds, and I'll have something off here to, let's say, so we'll do a couple different things in this one. This time I'll have an angle that is referenced to vertical instead of horizontal. We'll make that let's say a 30-degree angle. And the tension in this wire, we're going to have to make that just about we'll make that 2,600 pounds. There we go. So 2,600 pounds of tension in that wire, 30 degrees off of vertical. So let's add in another wire. This other wire is going to be anchored up to the ceiling here someplace, but we don't know what angle or what amount of force we're going to need in order to balance this out. And in fact, I'm going to change my numbers just a little bit here. I think we're going to bump the weight up to about, let's bump the weight up to 3,500 pounds. There we go. That's a little bit better weight. So let's see how this works. So here's the issue. We don't know anything about what's going on with this rope to the left. We don't know what angle it makes. And just like I did here for this rope, or this wire, I'm going to reference the angle to vertical rather than horizontal. So that's my unknown angle. And I have some unknown tension in that wire. And we need to find out what those two values are. Now, our instinct should kind of tell us that there's going to be some value of that tension and some value of the angle that will make this work. Because we've seen plenty of these systems wired up that we should be able to have equilibrium with this. We have two unknowns, which is the most we can handle in this type of problem. This is a concurrent force problem because all the forces intersect at this one point. And it's a coplanar system because it's all in the page. So there's our setup. Let's go ahead and draw our free body diagram first. And the free body diagram has to include what you're trying to find. So I can't just draw the free body diagram of the box because that would just be a weight pulling down and the tension in this rope pulling up. It wouldn't expose my unknown quantity. So we're going to use that connection point where all three of those ropes or those wires connect together. That'll be our body for our free body diagram. Now the box is pulling down on that point. It has weight. So the box is pulling down on that point. This rope is cut, or this wire is cut by that system boundary. So it's pulling down with 3,500 pounds of force. Over here to the right, I've got this 2,600 pound force at an angle of 30 degrees to vertical. And then I've got my unknown force, some tension and some angle. So there's our free body diagram. We've got to define a coordinate system, and we can put that anywhere that's convenient because we really don't care about where the origin is. All we want is a reminder of what directions are positive and what directions are negative. And to the right is positive and up is positive. The opposites would be negative. So there's our free body diagram. So we've exposed the forces that are acting in this system. The next step is to analyze the forces, break up the forces into components. Since we are interested in the sum of these forces and looking at what that sum does, the way we add vectors together is break them up into components and add the components together. So I'm going to label these, and I'm going to call this one vector 1, I'll call this one vector 2, and I'll call my unknown vector vector 3. Now vector 1 has an x and a y component. Vector 2 will have an x and a y component. And vector 3 will have an x and a y component. Now vector 1 is pretty simple. Vector 1 is straight down. So all it's got is a y component, no x component. So no x, 3,500 pounds of y. Vector 2 has both an x and a y component. It's pulling to the up direction and to the right. So it's pulling up and to the right. Be careful here. This is one of these places where if you're used to just kind of plowing ahead and jumping things into your calculator and not thinking about what your setup is, you can run into some difficulty. If you're used to thinking that I'm always using cosine to get x and always using sine to get y, you're going to flip up the components here. It's one of the most common errors I see made here. We've got an angle reference to vertical. Now, you certainly could figure out the complement to that. You could say, well, I don't like it referenced to vertical. I'm going to reference it to horizontal and change it to 60 degrees. There's nothing saying you can't do that. You certainly could, but it's a potential error if you make a mistake in figuring out that number. Certainly with 30 and 60, it's not too hard, but when it's 27.842, and you want to find out what that complement angle is, there's a possibility you could key something in wrong, or you could mentally screw up the math and end up with a bad angle. I always find it works out best if you use the numbers that are given to you and avoid unnecessary translation of those in an attempt to make the problem easier. So I'm going to keep the 30 degrees, and I'm going to remember that x doesn't always go with cosine and y doesn't always go with sine. What always goes with cosine is the adjacent side. Whatever side's adjacent will go with cosine of 30. Well, my adjacent side is y here. My adjacent side is the vertical piece. So my y component is going to be 2,600 cosine of 30 degrees. And my x component, that's going to be the opposite side. Opposite goes with sine. So I'll have 2600 sine of 30. Now, if you've been kind of brought up in math classes, essentially, this might get a little uncomfortable for you because you're used to really thinking about doing things by this very rigid framework of x going with cosine, y going with sine, and you might initially have some resistance to doing that. But you'll find that once you gain a little bit more flexibility in applying trig, when you can kind of take those artificial restraints that you're under in a math class off, you can do a problem much more easily. There's so much less overhead you have to deal with, and you'll be better off in the end for it. So let's go ahead and figure these out. 2600 sine 30. Hopefully I don't need a calculator for that one. That's 1300 since the sine of 30 is 0.5. Then I've got 2600 cosine of 30. That's 2251. And I'm going to say for this problem, I want to have 4 significant figures in my answer. So I want my answer good to 4 sig figs. There's nothing in the problem inherently that will tell me that, so I have to put it in myself. If there was something in this problem that indicated there was a limit to our measurement, that would be called out in the problem statement. I always make sure I'm very clear on that so that there's not a question as to how to handle significant figures. So in this case, we'll assume the problem said, make sure you have 4 significant figures in your final answer. That means that I need to keep 6 through my calculation. I might be able to get away with 5, but if I have a lot of rounding in the wrong directions, it could stack up enough to be a problem. So it depends on how many steps I have to do. So I always find a good general practice, so I don't have to think about it too much, is to always keep 2 more sig figs than what you want in the end. So I want 4, so I'm going to keep 6. So I'll have 2251.67 for my y component. Then we get to our unknown vector. Now we know nothing about this vector. We don't know the size, we don't know the direction. And whenever that's the case, don't try to use t sine theta and t cosine theta. It's just going to get messy that way. Instead, deal with the Cartesian components, the x and the y. So my x component is just going to be tx, and my y component is just going to be ty. And then just like the problem we did off of the homework, in the end, I'll draw my components out, and I'll figure out what my magnitude and direction have to be from the Pythagorean theorem and inverse tangent. So I would just call those tx and ty. A lot of times people get through this setup and they'll get to this point and they'll do t cosine theta and t sine theta, and then they'll crash because they have no idea where to go from there. They end up with the equations and they look ugly and they can't solve them. Tx and ty will be fine. They're just symbols. We can solve for the numbers for those and then work from the Cartesian components to the magnitude and direction. So there are the components here. So the next step is to do a sum. We need the sum of forces in the x direction and the sum of forces in the y direction. So I'll take my sum of forces in the x direction, and when I do my sums, I always leave out the signs. I just look for the magnitudes of the components. I put the signs in by referencing the drawing and what direction that component's in, throwing negative signs in as I need them. So I look at my coordinate system, I look at the drawing, and I look at the component. I'll throw in a negative sign if I need to. So in the x direction, well, I've got nothing from vector 1. Vector 2 has 1,300 pounds in the x direction, and it's to the right. So that's positive 1,300 pounds. And then I've got tx. Tx, according to my drawing, the tension pulls to the left and up. So the tension's pulling to the left and up. to the left is negative. So I would put in here minus tx. So if we had a number for tx, if tx was 37, we just subtract off 37. We only have the size here. We don't have the direction built in. So we have 1300 minus tx, the minus coming from the fact that we've essentially assumed this is pulling to the left. And that's an important point that we'll see in our next problem, that we've really made an assumption here. We know nothing about this particular vector. Based on the physics of the problem and how things lay out, we made a pretty good guess as to what direction that force needs to be in, but we might not be right. In some situations, we don't have enough information to tell easily what direction our force is going to be in, so we have to make an assumption. The math will tell us whether our assumption is right or wrong. And so that's an important idea. We're going to see here that our assumption is right, and I'll show you how to tell your assumption's right. So we've essentially made an assumption that this is pulling to the left. And we're using that assumption here when we write minus tx. We'll do our sum of forces in the y direction. I've got 3,500 down, so that's negative 3,500. I've got 2251.67 up, so that's positive 2251.67. And then I've got y, ty, pulling up. Again, by assumption, we've assumed it's pulling up. So we'll put in plus ty. So those are our sums of forces in the x and y directions. Now, if this system is in equilibrium, then both of these sums must be 0. Now that gives us two equations that we can solve. So let's solve the first one because that's kind of the easiest one to do. Now, hopefully at this point you're comfortable enough with algebra that you can solve these without too much difficulty, and that you can be very flexible in how you apply that algebra. What I would do here to solve this one, I just add tx to both sides. That'll give me an equation that says 1300 equals tx. Now, it's not wrong for you to subtract 1300 from both sides and then divide both sides by -1, but it's an extra step. And as you do a lot of these, you'll learn how to spot where you can be a little more efficient in solving. So we've got our unknown tx value. And something very important to note about that unknown tx value is that it came out positive. Now that might seem strange at first because tx is to the left. But this is what mechanism we use to check our assumptions. We assumed it was to the left, and we used the fact that it was to the left when we wrote this minus here. If your assumptions are correct when you set up a problem in your free body diagram and you use those assumptions in your equations, if your assumptions are correct, your answers will come out positive. So positive answers mean that you got all your directions correct. If your answer comes out negative, it means you assumed in the wrong direction for that component. So if my x component came out negative and I had assumed it'd pull to the left, it really pulls to the right. It doesn't change the number, but it changes the sign. So that's a really, really important idea to keep in mind here. Negatives mean incorrect assumptions. Positives mean correct assumptions. So it's a little bit different than the formal process of just adding vectors together, where if we got a negative component, it was to the left, and a positive to the right. That was when we were getting numbers. But here we're solving an equation. When our unknown comes out positive, it means we got the right direction. We guessed the right direction up here. If it came out negative, then it means we screwed up our guess. And it might seem strange looking at a problem like this that you could ever screw up a guess, but we'll see in the next problem that it's not always so clear. So 1300 to the left based on our assumption. For the next equation, We can simplify this down a little bit first here. We've got negative 3,500 plus 2251.67. And that's negative 1248.33 plus ty equals 0. And I would just add the 1248.33 to both sides. Now, since signs are very important here to telling us whether our answers are correct or at least have a chance of being correct, you got to be fairly careful with your algebra. I see sometimes people get to this stage and they try to do that last step in their head. And sometimes they lose the sign in doing it. It's not 100% of the time, but it's an easy place to lose a sign and get yourself flipped up a little bit. So I would work it out carefully until you're reasonably sure you're going to be able to do it correctly. So TY 1248.33. Now that also came out positive, which means we assumed the direction correctly. We assumed in our drawing that T pulls up, that TY would be positive, and it is, that TY goes in the upward direction. And our answer came out positive, so that means our assumption was correct. Now in the end, we want the tension and the angle. And be careful here. You've got to meet the specifications. You've got to answer the question that's asked. In this case, they ask for the magnitude and they ask for the direction measured from vertical. Don't just go over into what we did in problem 3 on the homework and draw X and then Y and then find your angle, because that'll give you the angle to horizontal and you'll be 90 degrees off of, well, you'll be 90 minus, you'll have the complement of the correct answer. So you've got to look at what you want and set your problem up to give you what you want. Always set up your vectors, set up your components to enclose the angle you want. So in that case, to draw this out, I'm going to draw out TY first. And TY is going to end up looking something like this. 1248.33. That's how much force is up from my unknown. And then I'm going to draw TX. 1300. So laying that on top of the drawing here, you can see a little bit of what we're looking at. We've got, well, that's not right. Let's try a different one there. There's TY and TX. So we're just building this vector, we're building this resultant vector out of TY and TX. We want this angle, so we've got to make sure it's inside the triangle. So that's what I've got set up down here. Now my resultant is right there. That's going to be T with my angle. So we've done all the math really to get us our values. Now we're just cleaning it up. We're taking that last step we need to get the answer that the problem is asking for. So we can use the Pythagorean theorem to get the tension. That's going to be the square root of 1300 squared plus 1248.33 squared. And we calculate that out. I'm getting 1802.31. And that's pounds because this is a force. To get the angle, we use inverse tangent, but it's always inverse tangent of opposite over adjacent. It's another place where you don't want to get stuck thinking about x's and y's. If you're used to thinking inverse tangent is y over x, you're going to run into problems in problems like this where you're referencing to vertical. Inverse tangent of opposite over adjacent. So our angle is going to be inverse tangent of opposite 1300 over adjacent 1248.33. So opposite 1300, adjacent 1248.33, and inverse tangent. So there I get 46.1616 degrees. And we're almost there. We're 98% there. The last thing we have to do is state our final answers. So now is when we round to our final number of sig figs. We wanted 4 good sig figs in the problem, so we'll round both of these to 4 sig figs. So our final answer, tension, is 1802 pounds. Don't forget your units. And the angle is 46.16 degrees. And always a good idea to box in those final answers so that it's really clear to whoever's reading it that this is the answer you want. So 1,802 pounds at 46.16 degrees. Anything not quite making sense on that one? All right then, so let's try another example. This one is something that comes up in some of the more sophisticated problems we'll do later on. And I'm going to kind of jump right to the free body diagram on this one. So I've got this point. We'll find out that it's actually a pin. It's a pin that holds part of a structure together. And it's going to have a bunch of forces acting on it. It may have a force of, let's say 50 pounds in that direction. Maybe it'll have 90 pounds that way. Maybe we'll have something off to an angle here. We'll make that, let's say 60 degrees. And we'll make that let's make that we'll make that 45 pounds. And then we're going to add a fourth one in here. We're going to have some fourth force that we're not entirely sure about what direction it's going to be in. Because how this 45 pounds interacts with these other two is not quite clear. So let's assume our unknown force is over here, because it kind of looks like that'd be the direction it'd be in. We've got these 4 forces pulling against each other. It's not an unreasonable direction to assume. And we'll put an angle down here. So there's our problem. We have had to guess about what direction F is in. It's not clear whether F should be above or below the horizon. It's not necessarily clear based on the numbers here until you start calculating things, what direction, whether it should be to the left or the right. So I've made a guess here essentially just based on convenience because it's the cleanest place to draw it. There will be other reasons we make assumptions later on based on a structure, but the basic idea is sometimes we just have to make a guess. And when we have to make that guess, we have to let the math tell us whether our assumption is right or wrong. So let's see how we did on our guessing on this one. So let's go ahead and label these. I'll call them vector 1, vector 2, vector 3, and vector 4. We'll define our coordinate system. to the right and up are positive. Well, vector 1, vector 2, vector 3, and vector 4 are all going to have components. So we can break those up. Just like every problem, we're just doing vector addition. For vector 1 straight up. So it's all y component, no x component. So it's 90 up and nothing to the side. Vector 2 is all x, no y. 50 to the right, nothing up or down. Now vector 3, that's off at an angle. It's to the left and down. So that one we'll have to figure out. We've got our adjacent side, that'd be x. So our adjacent side is cosine. X will be given by cosine here. It'll be 45 cosine of 60. And that'll be 22.5. And then we have our y component. Y component's going to be opposite here, and opposite goes with sine. So we'll have 45 sine of 60. And that is 38.971. And I'm going to assume here 3 sig figs are what I want in my final answer. So 38.971, and that'll be down. All right, now then we come to vector 4. Now vector 4, we don't know anything about it. We don't know size, we don't know direction. So just like the other problems where we don't know anything about it, we'll just label it with its components in the Cartesian system, fx and fy. And we'll go back later and figure out the angle and the magnitude. So there we've got our forces all broken up into components. Now we need to do our sums. So we'll take a sum of forces in the x direction. And going through our tally here, there's nothing in the x direction from vector 1. We've got 50 to the right for vector 2, so that is positive. For vector 3, we've got 22.5, but that's to the left. So minus 22.5. And then we've got fx, the x component of our unknown vector. Well, we've assumed that pulls to the left. So we have to draw it in negative, or we have to put it in the sum negative. So we have 50 to the right, negative 22 or 22.5, and fx both to the left. Do our sum of forces in the y direction. We've got, from vector 1, we've got 90 up, so positive 90. From vector 2, we've got 38.971 down. So negative 38.971. And then we've got fy, and we've assumed fy pulls up. So we'll put in plus fy. So there we've got our sums. If this point is in equilibrium, then these sums must add up to 0. So we can say those two sums are 0, and that gives us two equations that we can solve. For the x direction equation, if we first simplify the numbers, 50 minus 22.5, that gives us 27.5. And really watch your signs here, because if you mess up your signs, you're going to get an incorrect feedback on whether your assumptions were negative or positive, were correct or incorrect. So be really careful with your algebra on these. Well, here I get 27.5 minus fx. I'm going to add fx to both sides. And that'll give me, writing it up here, 27.5 equals fx. or flipped around, same thing, Fx equals 27.5, and that's pounds. So we have a positive result. That means our x direction assumption is good. Vector F, our unknown force, really does pull to the left. It has to. So a positive result confirms your assumption. So we have the right direction nailed down for the horizontal component of our unknown force. Let's see how we did on the vertical. Well, if we clean up the numbers a little bit, 90 minus 38.971 is 51.029 plus Fy equals 0. Well, if we subtract 51.029 from both sides, we'll get that Fy equals negative 51.029 pounds. That one came out negative. And this is where you might need to think about it for a little bit, because a negative doesn't necessarily mean that we're up or down or left or right. A negative means it's opposite the way you drew it. So while with a y component, we usually assume negative means down, what it really means here is it's opposite the way I drew it. I drew it up. I drew it so that it was pulling up. That was an incorrect assumption. It really pulls down. So vector F pulls to the left and down instead of to the left and up like I assumed it did. So here's how we can finish up our problem. We can find our magnitude and find our direction, taking into account this negative. So I'm going to redraw it. Since I'm dealing with a angle reference to horizontal, I'm going to go x first, then y. I know my x component is to the left, and it's 27.5 pounds. I know now my y component should be down, not because I got a negative here. It means it's opposite the direction I assumed. I assumed up, so it's actually down. So there we've got our y component, maybe a little longer to scale here. There we go. Could be longer, but I'm running out of paper. So 51.029 down. And then our resultant's going to be over here. Some angle and some force. So we'll get our magnitude from the Pythagorean theorem. We'll take 51.029 and square that. We'll take 27.5 and square that. Add them together, take the square root, and we get 57.967 pounds for our magnitude. Our angle, inverse tangent of opposite over adjacent. So 51.029 divided by 27.5, inverse tangent, got to actually divide first, 27.5 divided, and inverse tangent. There we go, that's a better number. Angle 61.679 degrees. And we know now that that angle is below horizontal. Now this would be a sufficient drawing to answer the question. Because the drawing's there and it clearly shows the angle is below horizontal, you can just state the number alongside the drawing. We do have to round to the correct number of sig figs here, and in this case that was 3. So 57 point, well, it's going to be 58.0 on that one. And our angle 61.7 degrees. Now, if you really want to be clear about it, you can go back and redraw the free body diagram to make sure that it's clear what it should have looked like if you made the right assumption at the beginning. It's not necessarily something you have to do, but it's not wrong to do it. So you got these 50 pounds and the 90 pounds here. You got your 45 pounds. At 60 degrees. And then you've got this other one here, which is a little bit harder to draw in the right angle and all that. But you've got this other vector that's got an angle here of 61.7 degrees and has a magnitude, if we drew it out to scale, it'll be down here somewhere, 58.0 pounds. So looks like that vector down to the lower left needed a good bit more help to counteract this 50 and this 90 pounds than just the 45 pounds at 60 degrees. Wasn't quite enough for it, so we had to have a lot more force pulling down in that direction to balance everything out. So that'll come up in a lot of problems where we'll have to make an assumption about what direction the force is in, and we may not have enough information to know what direction is right. So we have to let the math tell us. And the way the math tells us is by giving us negative values for our unknowns. Negative values for the unknowns means that that the correct direction is opposite what we assumed. Anything not quite making sense on that problem? All right then. So let's set up our next problem here, and in the next one, we'll be taking a look at a situation where we're going to need a little bit more mathematical skill than what we've necessarily had to use so far. This is about the hardest as far as working out the math goes. It's about the hardest we get in the in this class anyway, as far as working out these types of problems go. So I'm going to set the problem up, then we'll take a break, and we'll finish up that problem in the practicum. So let's go back to the box on a wire problem. So the box on a wire problem can be set up in a lot of different ways. So we'll use it for that. So here we've got 2,400 pounds of weight we've got to support. Sounds simple enough. Well, let's have a couple ropes supporting that. All right, not looking too bad so far. We're going to have some angles involved here. Let's say this one's at 40 degrees. And that one's at 30 degrees. And we'll have tension in rope 1 or string 1, line 1, and tension in line 2. Now, at first, it might not look all that different than the problems that we've solved so far. And in a certain sense, it really isn't. It's still a coplanar system. It's still a concurrent system. It has two unknowns. Instead of unknowns, though, being the magnitude and direction, now the unknowns are two magnitudes. We have the directions all locked down. We know what they are. So this is going to have some consequences in our analysis. We'll see how it looks different than the way that we normally would see it in the problems, at least that we've done so far. So let's start it out. Let's draw the free body diagram. So the free body diagram, we'd have our central point. We got 2,400 pounds pulling down. We have this unknown force T1 at 40 degrees from horizontal. we have this other unknown force, T2, at 30 degrees from horizontal. Now there is a value for T1 and for T2 that will make this work. We just have to figure out what that value is. So let's go ahead and label the vectors. We'll have vector 1, vector 2, and vector 3. And each of those is going to have components to them. So we have vector 1, x and y, vector 2, x and y, and vector 3, x and y. Well, vector 1's easy. It's pulling straight down. Don't forget the coordinate system. Pulling straight down, it's all y. So 2,400 pounds down, no pounds to the left or the right. Then we get to vector 2, which is this T1 at 40 degrees. Well, with that one, we have a bit of an issue. In the previous problems, we knew if we knew nothing about the problem, we could just use Tx and Ty. We could use the two components. That won't work here because we don't know. We do know something about this vector. We know the direction. So when we know at least one piece about the vector, it's always going to be best to use sine and cosine. It minimizes the number of symbols that'll be in the problem. So for the x component for T1, that's the horizontal piece, that's the adjacent side, so it's going to go with cosine. If I had a number for T1, I'd just say multiply that number times the cosine of 40. So that's all we'll do here. We'll do T1 cosine of 40 degrees. Vector 2's y component is the opposite side. Opposite goes with sine. So we'll say T1 sine of 40 degrees. And we'll do the same for vector 3. The horizontal piece is x adjacent, so goes with cosine. So we'll have T2 cosine 30 degrees, and we'll have T2 sine of 30 degrees. Those are the components of our vectors. Usually when people get a problem like this, after we've done the examples we've done so far, they try to go, well, T1x and T1y, T2x and T2y, and then end up with with two equations with four unknowns in them. And that doesn't work. You can do that when you know nothing about one vector. But when you have one piece of information about the vector, it's always going to be best to use sine and cosine. So we still have two unknowns here. T1 and T2 are the only missing pieces. So to set up our equations, we'll have to take our sums. So we'll take our sum of forces in the x direction. And got nothing from vector 1. From vector 2, that's pulling to the right. So positive T1 cosine of 40 degrees. Vector 3, that's pulling to the left. So minus T2 cosine of 30 degrees. For the y direction, we've got negative 2,400. We have T1 sine 40, and that's up, so positive T1 sine 40 degrees. And we have T2 sine 30. Now, since this is an equilibrium, the sums must equal 0. So that gives us two equations. And I'm going to rewrite those down here, cleaned up just a little bit. I'm going to leave the first one alone here. I'm just going to say T1 cosine 40 degrees minus T2 cosine 30 degrees. That equals 0. I'm going to add 2400 to both sides on this equation, on the y direction equation. So it'll say T1 sine 40 degrees plus T2 sine 30 degrees equals 2400. So there we've got our equations of equilibrium. There's a bit of a problem there. In every example we've done so far, once we got to this point, we just had to solve the equations. We had one unknown in each equation. The equations were separate from each other. It didn't even matter if we solved the first equation or the second equation, one before the other. These equations are connected. They're what we call coupled together. They're entangled. You can't solve one without the other. This is a set of simultaneous equations. This is why we had to learn how to do simultaneous equations a week or so ago, a couple weeks ago. Simultaneous equations show up in these problems, and there's not always a way to get rid of them. In some situations, some limited situations, you can play some mathematical trickery to get rid of a simultaneous equation. You can kind of rotate things so that the equations become a little simpler. But that's not always possible. So we end up having to solve simultaneous equations. So that's the setup. We'll take a look at the solution to this when we get back from our break. So let's take a bit of a break, about 10 minutes. We'll come back and we'll move into our practicum session. All right, recording's paused. Or yeah, is it? Crap, I'm gonna have to edit that now. All right, let's resume. So I've transcribed our equations of equilibrium over to another page just to make to give us a little more space to work in. Think back to what we did with simultaneous equations a couple weeks ago. We had two equations. We wanted to combine them together in some way so that we could eliminate one of the unknowns. And the easiest value to eliminate, the easiest unknown to eliminate, was one where there was already a built-in sign difference between the two equations, where the unknown shows up positive in one equation and negative in the other. Well, if we look at the equations we've got here, T2 shows up with a sign difference. So that would be our target for elimination. So the next step is to get the coefficients to be the same. We found that when we had a negative and a positive, a built-in sign difference, if we could make the coefficients of the unknowns to eliminate the same but have an opposite sign, we just have to add the two equations together. And with whole number simple equations, you can usually find a multiplier, kind of like a common denominator, to figure out what to multiply the first equation by and what to multiply the second equation by. But that's math class stuff for the most part. For realistic problems, we have pretty ugly coefficients here. In fact, let's go ahead and get rid of our sines and cosines and just make them into numbers. So we'll rewrite the equations a bit here. Cosine of 40 is 0.76604. So rewriting the first equation, that's 0.76604 T1 minus cosine of 30 is 0.86603 T2 equals 0. So that's our first equation rewritten. And the second equation, we've got T2 sine of 40. That's 0.64279. That's T1 plus T2 sine of 30. Well, at least we get a kind of nice number there, 0.5 T2 equals 2400. So there's our equations, just changed from sine and cosine symbols to numbers. So it looks pretty ugly. We're not likely going to find a multiplier, something we can multiply the top by and multiply the bottom by to get the same number sitting out in front of here, in front of T2. In fact, this number involves a square root of 3, so it's not likely to have anything interesting show up that would be able to multiply through by. There are irrational numbers involved. Unlike with whole number simultaneous equations, where we leaned a lot on multiplication, here we can lean a lot on division. Division and multiplication work the same way when we apply multiplication or division to an equation. As long as we do the same thing to all the terms on both sides, it won't change the equation. It'll change what it looks like, but it won't change the value. So since I want to make the coefficients the same in front of T2, the easiest coefficient to make is a coefficient of 1. If I take my first equation and I divide it through by 0.86603, so divide each term by that, I'm still going to have an ugly number out in front here. I'll have 0.76604 divided by 0.8663, so 0.76604 divided by 0.86603. That gives me 0.88454. So I get 0.88454 minus, since I'm dividing by positive 0.86603, 0.86603 divided by 0.86603, that's just 1. So I get minus T2, and 0 divided by pretty much anything is 0. So that simplified the equation a little bit. We've got at least a simple coefficient in front of T2. Well, we can do the same thing in the second equation. The coefficient of T2 in the second equation is 0.5. So if I divide each term by 0.5, that will leave a plus 1 T2. So first term, we'd have 0.64279 divided by 0.5. That's 1.2856. Oops, and I made a little bit of a mistake here. I just forgot I lost my variable. So this has a T1 in it. So it's 0.888454 T1 minus T2. I'll write these down a little more cleanly a little bit further below once we're done with them. So this is T1, 1.2856 T1 plus T2 equals 2400 divided by 0.5. That's 4800. So let's go ahead and transcribe those here. We've got 0.88454 T1 minus T2 equals 0. That's our new x direction equation, our new first equation. And our new second equation, 1.2856 T1 plus T2 equals 4800. Well, a lot of other things might look kind of ugly, but at least we've got a positive 1 coefficient in front of T2 and a negative 1 coefficient in front of T2. If we add these two equations together, the T2s will cancel out. So let's go ahead and do that. On the right-hand side, it's just 0 plus 4800, so that's 4800. The T2s cancel out, and then I end up with 1.2856 plus 0.88454 And that'll give me 2.1701 T1. Well, that's an equation we can solve. We've got a coefficient times an unknown equals some number. So we divide both sides by 2.1701. And T1, 2.1701, 2211.9. So 2211.9 pounds. Rounded to 5 sig figs for now. We're going to round to 3 sig figs in the end. So that's my value for T1. Now that we have one value for T1, we can go back to our original equations and plug that in and solve for T2. And looking at the original equations, I wouldn't go all the way back to here because we're just going to repeat some work there, but I'd go to this one here. I'd probably use the x direction equation for that since it's a little tiny bit simpler. I don't have a number over on the right hand side. So if I go and plug that in, I've got 0.76604 times my value of T1 minus 0.86603 T2 equals 0. So if we multiply that out, we've got 0.76604 times 2211.9. That's 1694.4 minus 0.86603 T2 equals 0. I would probably add the 0.86603 T2 to both sides. That'll leave me with just 1694.4 on the left and a positive 0.86603 T2 on the right. And then we can finish it up by dividing both sides by 0.86603. So 1694.4 divided by 0.86603. So T2 is 1956.5 pounds. So ugly simultaneous equations to deal with, but they work. And it doesn't get any more complex as far as the basic mathematics goes. It doesn't get any harder than basically solving a set of simultaneous equations that looks like this. So if you can handle this, you can handle any problem that you might have come at you. So it's just a matter of figuring out which variable you're going to eliminate, using division to get the coefficient to be 1, but the signs to be different, and then eliminating that value. So let's finish the problem here. We can go back to our original page. T1 we found was 2211.9, and we're going to round to 3 sig figs, so that would be 2210. So T1 was 2,210 pounds. And T2, 1956.5, that'd be 1960. So T2, 1960 pounds. So there's our final answer. Remember, those trailing zeros don't count unless there's a decimal point. So 196 and 210 or 2210 both have 3 sig figs. Now, it's worth taking a look back at the problem and making sure that it makes sense, that the answers are what we've got. If we take a look at the numbers, we got a slightly higher value on T1 than we had on T2. we'd expect if these two angles were the same, we would expect an even split. If the angles are the same, then both are going to be pulling with the same amount of force. So it would be an even split of the load, whatever that force happened to be. If there's angle differences, though, we'll see different amounts of load. The part that is going to bear the most is going to be the more vertical of the piece, the one that's closer to pulling straight up. Well, if we look at that 40-degree angle, that's 10 degrees steeper than the 30-degree angle. T1 is pulling up more than T2 is. So it makes sense that T1 is carrying more of the load. Now, that may not help you as far as actually going and solving the problem, but it does help to give you a bit more intuition about how these structures work and where you should expect high loads and where you should expect smaller loads. So it's worth going back and taking a look at the problem after you've got your final numbers and at least verifying that it makes sense, reasoning it out, saying, well, I can see why this part would have more force on it than this other part would. That's really useful out there in the field, where in many cases you're not immediately doing the calculations. You're just looking at a structure and trying to figure out, where's this going to break? Where is this going to max out first? And then figuring out what you might have to do to either size it out and make the structure strong enough in that area so it doesn't fail, or maybe redesign it. So that's about the most difficult kind of equilibrium problem, this type of equilibrium problem we can get. Any questions on the solution on that one? All right then. Well, let me go ahead and put a couple problems up here for you to try out on your own. First one here will make relatively straightforward, I suppose. Let's do something that looks sort of like this. We'll have force there. Call that force 1. Force 2 at 30 degrees, and then maybe go 27 degrees, and we'll make that nice even 1,000 pounds. All right, so given what you've got in this problem, which is actually setting you up, this kind of problem you're going to be solving a lot of later on when we get into things like truss analysis. This kind of problem comes up all the time. So take a few minutes, try and set that up, try and get it worked out, and figure out what the values of F1 and F2 must be. Let's say, let's get our answers to 4 sig figs. All right, I'll pause the video and give you a few minutes to get some work done on it. If you're hitting a stopping point or something where you're not sure about how to set it up, go ahead and ask the question. All right, so let's take a look at the solution here. So we've already got our free body diagram. All we need to do is define what our coordinate system is going to look like, and we'll use X and Y there. Standard setup. We've got our 3 vectors here, so we'll use, we'll identify F1 as vector 1, F2 as vector 2, and our 1,000-pound force as vector 3. So each of these will have components. Now, fortunately for us, vector 1 is in a nice direction. Although we only know the direction, we don't know the magnitude. We at least have it lined up with an axis. So there is no x component all the magnitudes in the y. So we don't need to worry about sine or cosine or anything like that there. F2, we really can't do anything else with other than use sine and cosine because it's at angle 30. So its x component is the horizontal piece or the adjacent piece. Adjacent goes with cosine. So we'd have F2 cosine of 30, which will end up being, if we work out the numbers, 0.86603 F2. And then for the y component, that's the opposite side. Opposite goes with sine. So we'd have F2 sine 30 degrees or 0.5 F2. And then for y, or for vector 3, we've got our angle to vertical instead of to horizontal. So got to be careful and make sure that we get the right components there. The x component would be over here like this. The y component's up like that. So the x components are opposite side this time to the 27. So the x component's opposite goes with sine. So this would be 1000 sine 27 degrees. And since we want 4 good sig figs in our final answer, we're going to keep 6 out of our anything we round. So to round that out, I get 453.990. And then for y is our adjacent side. Adjacent goes with cosine. So 1000 cosine 27 degrees. And that's 891.007. So there we've got our forces broken up into components. Next, we have to do our sums. So we'll do our sum of forces in the x direction. Well, vector 1 has no x component. Vector 2, its x component's to the right, so that'll go in positive. So vector 2's x component is 0.86603 F2, and that's going in positive. Then vector 3, that's pulling to the left. So its x component goes in negative. So we have negative 453.990. So there's our sum of forces in the x direction. If we do our sum of forces in the y direction, well, vector 1 is all y and all negative. So that goes into the sum negative F1, since it all pulls down, whatever it is. Vector 2, its y component is up. So it goes into the sum positive. So we'd have positive 0.5 F2. And then for vector 3's y component is up. So we get a positive 891.007. So there we have our two sums. Sum of forces in the x direction and sum of forces in the y direction. Now, if this system is in equilibrium, then the sums must equal 0. And that gives us our two equations. And we're a little luckier in this problem than we were in the last one that we worked out. In this one, we've got a set of equations that we can solve without mixing them together, without eliminating anything. Because although we can't solve the y direction equation, we have too many unknowns there, we only have one unknown in our x direction equation. So that'll let us solve for F2. So we'll be able to get F2 out of this. And then once we have F2, we can plug it into the y direction equation and solve for F1. So let's go ahead and do that. So to solve the x direction equation, I'd add 453.990 to both sides. So I'd get 0.86603 F2 equals 453.990. Then I divide both sides by 0.86603. So we'd take 453.990, divide it by 0.86603, and we'll get 524.220. So F2 is 524.220, and that is pounds. Now it's worth taking a look at it and saying, well, this did come out positive. That means that we have the right direction here. We didn't really have a lot of choice. It has to be up and to the right because it's got to cancel out the down from F1, and this other vector isn't enough up to necessarily cancel it out. So at the very least, we know we have to be good to the right, and that we've got our angle locked down, so we really don't have to worry about whether or not our directions are good. We can go into the y direction equation now. We can plug in 524.220 in place of F2. So we have negative F1 plus 0.5 times 524.220 plus 891.007 equals 0. Well, crunching the numbers down a little bit, we've got 0.5 times 524.220. That's 262.11. So we have negative F1 plus 262.11 plus 891.007 equals 0. So plus. And we can combine the numbers together. 262.11 plus 891.007. That's 1153.12. So we have negative F1 plus 1153.12 equals 0. Well, easiest way to solve that one, at least as far as I'm concerned, is to add F1 to both sides. And then we get 1153.12 equals F1. So there's F1 and F2. And that also came out positive, so we know our drawing is good. So last step is just to go and present our final answers. So we can write those up here, rounded to 4 sig figs. 4 sig figs, F2 is 524.2. And don't forget the units, pounds. It's okay if you ignore the units within the problem, but when you're presenting your final answer, you've got to have those units there. F1, we had 1153.12, so that'll be 1153 pounds. There we go. So if we've got 1,000 pounds pulling up and to the left at about 30 degrees from horizontal, about 27 degrees from vertical, and another force pulling up and to the right at 30 degrees, and something pulling down to counteract them, we need 1153 pounds pulling down, and we need 524.2 pulling up and to the right.
I had most of it, but I got a sign wrong and earlier step and
Yep.
it threw everything off.
Yeah, you got to watch those sign errors. And a lot of times, if it's just not working out, it's best to just kind of go all the way back to the beginning of the problem. And if you have a sign error up here somewhere and then you get muddled in it down here, you could spend a lot of time looking for that sign error where if you just go and start the whole thing again and step through it carefully, you'll spend less time. Can't tell you how much time I've wasted just trying to figure out where did I go wrong down here when I could have just started the problem again from the beginning and saved a lot.
No.
All right. Any other questions?
Nope.
All right. That should be it for tonight then. Have a good night.
Okay, you too. Have a good weekend.
Thank you. You too.